Today we're going to talk about understanding Earth's climate and how it is changing. Conditionally, you should know that I'm a climate scientist, so that's the perspective I'll be sharing on this topic. The entire presentation's been broken down into sections, and I want to review those briefly so you'll know what to expect. I'm going to share some thoughts and perspectives on weather and climate in general, then talk about the disparity in climate change. A very important undercurrent whenever you deal with climate change is that it's moving at a different pace around the Earth's surface. Thirdly, we'll talk about some regional climate features that are changing in the Western Great Lakes region of the country. Then we'll talk about the consequences of those changes that are already being measured. And lastly, we'll talk about extremes, which after all have the most and greatest impact on our society. Weather is the condition of the Earth's atmosphere at the moment. It is commonly described by attributes such as temperature, precipitation, cloud cover, wind direction, and a number of other features. It is used in the science of meteorology to take the current measurements and frame them in a model context so that we can know what tomorrow's weather might be or next week's weather might be. Climate is more of a composite view of the environment around us. It is indeed the same attributes that we talk about in weather, but it's describing the climate or the behavior over a period of time and across geographic differences. The other real important feature with climate is to note that it is the end result of the interaction between the atmospheric attributes and the Earth's surface attributes. That's what gives us the climate, the long-term averages and the seasonal patterns and things of that nature. That's very important to understand the distinction between those two. Another important perspective on weather and climate is that the Earth's climate, Earth is 4.5 billion years old. The Earth's climate has been in a continual state of evolution. It's been forever affected by a number of drivers. It's affected by the sun and long-term variations in solar radiation from the sun. It's affected by changing Earth features, waxing and waning of ice cover, for example. Also changing ocean circulation patterns. It's occasionally massively disrupted by, for example, we all know about asteroid impacts that have occurred in Earth's history and impacted, for example, the demise of the dinosaurs and things like that. And so our entire history of the planet really suggests a story of an ever-changing climate relative to the planet Earth. That climate behavior that we now so emphatically measure with all our modern technology and instrumentation has been driven over time by categorically three drivers. One is the natural drivers, which I just alluded to, which is the geometry of the Earth and Sun relationship, occasional asteroid impact, ocean currents, etc. Two other drivers of Earth climate behavior, though, are tied to the human race. And those are changes that have been made to the Earth's landscape, such as, for example, commonly urbanization of an area where we've changed the configuration of the Earth's surface by urbanizing it and putting a built environment on the Earth's surface, if you will. Another is the extraction of resources from planet Earth in areas where we've done a lot of mining, deforestation, taking out wetlands, transforming landscapes to a managed agricultural setting, a number of other features. And that affects the interaction with the overlying atmosphere. So in reality, then you get a change in the climate attributes. And then that third category is, of course, the one most commonly talked about in the modern era, which is the changing composition of the Earth's atmosphere, driven dominantly by what we put into the Earth's atmosphere, the emissions that we produce in our industrial society. So the final word on this is that the Earth's climate and its behavior is driven by all three of these categories, and in composite they all have some measurable impact on the Earth's climate behavior. Our perspective of this behavior is also relevant in the context of understanding how we perceive this behavior. Across the last couple of centuries, climate scientists have perceived Earth's climate behavior with four distinct perspectives. This first one here that we call the stationary perspective dates all the way back to the founding fathers of our country, in that it is fundamentally based on measuring climate attributes such as temperature and precipitation, for example, at a point on the Earth's surface, day by day, year by year, over a period of time. And then after we build up a sufficient period of time, we can describe that climate's central tendencies, its means, its mode, values, etc., its seasonal variation, and its extremes. So Thomas Jefferson, for example, George Washington, Benjamin Franklin, many other founding fathers believed distinctly in this perception of climate behavior. There's also areas of the world where there's a strong perception of cyclical climate behavior, although that is mostly in the equatorial regions of the Earth's surface, which are dominated by cyclical behavior with the changing of the sun angle and the seasonal changes. And in fact, there is substantial statistical evidence that says that in those regions we do have distinct hot and cold periods, distinct wet and dry seasons, and things of that nature. We don't talk about the cyclical perception of climate behavior much in our region of the USA because, quite frankly, we don't see it. We don't see it play out here. A third perception of climate behavior, which is more of a 20th century perception, is that climate behaves over periods of time with changes or phase changes, if you will, in variability. This is kind of a modification of the earlier stationary view of climate behavior, in that it recognizes that over time, the variability around the central tendencies of climate waxes and wanes. Simply stated, we go through periods where it appears like the climate is stuck in a rut, and one year is like the next, like the next, like the next. And we also go through periods where climate behavior is highly erratic. One year is distinctly different than another. And so we have this amplified variability playing out in the climate behavior. And then lastly, and more relevant to this presentation, is the trend shift view of climate behavior, which argues the point, and very effectively, that if the climate is disturbed, for example, we continue to put greater emissions into the Earth's atmosphere, we continue to disturb the Earth's surface in terms of development and exploitation of resources, that we will alter the climate in terms of its interaction between the Earth's surface and the atmosphere. And in the end, what we'll do, graphically depicted here, is that we'll change the central tendencies in some meaningful way, and we'll also change the extremes in variability. And suddenly the measurements that we derive from the same point on Earth will start to look different than what the previous history has looked like. There will be behavioral changes outside the realm of what the history at that point on Earth has shown. So that's the trend shift perspective. 3 reasons to believe and hang our hat on the notion that the climate of planet Earth is indeed changing. I think these are important reasons. Certainly those of us engaged in climate science strongly believe in these reasons. The first is that the measured attributes, the temperature, precipitation, wind, solar radiation, etc., in 3 independently derived global data sets all show measures of change. Not only do they all show measures of change, we know that these changes are not random. These, in scientific terms, are statistically significant changes. Secondly, the models we use to mimic the Earth's climate system all fit the measured data, especially over the last 100 to 150 years, if we incorporate in those models the changes brought to the landscape by the human race, the changes brought to the composition of the Earth's atmosphere by the human race. And when we incorporate those, we know our models fit the measured parameters of the Earth climate system much better. And thirdly, the observed and measured physical and biological consequences that are increasingly being documented in recent years fit the measured changes in the climate attributes. So we know that the changes that have already occurred in climate behavior and, for example, precipitation behavior are already being played out in showing consequences to local landscapes and local behavior of weather systems. Now I'd like to transition to our second topic about the disparity in the climate change signal. This is an important undercurrent theme that I think should be recognized by all of us. The climate is changing on planet Earth, but it's changing at a different pace in different places. And so, for example, what I'm showing you in this slide is the observed surface temperature change that's occurred over the period 1901 to 2010. And the color coding depicted here across the Earth's surface is just a depiction of the disparity in the magnitude of that temperature change. So what I'd like to illustrate to you in the northern hemisphere here is that the mid to high latitude landscapes in the northern hemisphere are changing with respect to temperature at a pace that is faster and more profound than what we see in some equatorial latitudes of the Earth climate system. Secondly, I'd like to point out to you that overall we're seeing more change in the northern hemisphere of the Earth's climate than we are in the southern hemisphere. So there's disparity in the signal change. There's also disparity in the seasonality. When we look at the seasonality and how the seasons are changing across the Earth and the various oceans and land masses, we see disparity. For example, if we take North America, let's take and concentrate on North America. Here's a depiction of the temperature signal change for the months of March, April, May, the North American spring. And we see by the color coding on this that the colors are of a light pink hue, indicating relatively diminished temperature change. Even in the central western Great Lakes region of North America, we even see that the temperature change has been negative in some areas. But let's, for example, in contrast, then look at the northern hemisphere winter season, December, January, February, when we're dominated by long nights and short days. And what do we see in the temperature signal change over North America? Emphatically, we see it more profound. The pinks are deeper. In fact, there's even red hue tied to this, indicating a more amplified change in the temperature signal. Important point being here that there's change in the temperature signal, but it's disparate across the seasons. It's not the same across all seasons, and that disparity doesn't play out the same way across all the continents or the ocean basins either. Here we can dissect the temperature signal change and look more specifically at the USA. And what we see in the temperature signal change within the USA is, again, this disparity magnified to look at it, for example, among states. And the feature here I'd like to point out to you is that in the western Great Lakes region of the USA, you see a color coding that corresponds to a more amplified temperature change. In fact, arguably in the western Great Lakes, we're seeing a pace of temperature change that exceeds much of the rest of the country. And for example, to contrast with what they're seeing in the southeastern U.S. states, they're even seeing some negative temperature change in their landscapes. So that's another feature to point out, and I think in terms of the attention given to the topic of climate change and the way it's playing out in our country, we even see disparity in the public attitude. And I would argue that the public attitude in our region is more acute because we're observing more significant temperature change in our region of the country. Similarly, we look at the disparity in the signal change in precipitation. These data put out by the Intergovernmental Panel on Climate Change in the fifth assessment, most recently produced just over the last year, show that we have some regions of the globe where the precipitation is increasing, highlighted by the blue hue on these maps. And we have some areas highlighted by the brownish hue where the temperature is diminishing. The average annual precipitation is diminishing. So we have disparity in the precipitation signal as well. If we again dissect that relative to the states within the USA, we again see that in the western Great Lakes region of the country, where we see the deeper green hue associated here, that the precipitation change is of a greater amplitude than it is in many other areas of the country, so that we're seeing measurable change in precipitation that is greater than many other neighboring states. Finally, those in the other sciences other than climate science, for example, the biological sciences and the geosciences, are measuring consequences of these changing climate attributes, and with each passing year, the number of consequences is growing in volume. We're seeing changes in lake behavior, notably in the high latitudes, the duration that lakes are ice covered in the winter. We're seeing changes in bird migration patterns, for example, birds that migrate between the high and the low latitudes. We're seeing changes in ecosystems in terms of the phenology of those ecosystems and when, for example, plants are budding out and flowering in the seasons and when they're dying off in the autumn. And all of this is documented in much of the IPCC literature year after year, a building volume of evidence that the climate attributes I've alluded to earlier that are changing with statistical significance are playing out and having real consequence in the other features of the Earth's climate that we measure. One that's talked about perhaps as much as any is the changing in the high latitudes, and particularly the changing in Arctic sea ice. The National Ice Center reports to us that in 2012, the extent of Arctic sea ice reached an all-time low value in the context of the historical measurements there by the satellite systems, which date back to 1979. So that the overall depiction here, for example, in the map shown, is the shrinkage of ice cover in the polar Arctic that was achieved by mid-September of 2012, which was well below the average values for that time of year, and in fact set an all-time low value. So that's another important feature and is playing out in a variety of ways in terms of changing the ecosystems of the Arctic. The greenhouse gas emissions continue to go up unabated. In fact, a report recently suggests that the pace of carbon dioxide change in the Earth's atmosphere is equal to or exceeding the measurable pace that we've measured over the last few decades. We've now approached and at times exceeded 400 parts per million, according to the data kept by the National Oceanic and Atmospheric Administration. The temperature pattern, which has been correlated to those emissions, has shown increase across time as depicted in this graphic. Again, as I said earlier, we have independently derived global temperature data sets that show this. Much has been made out of the plateauing, if you will, of the last few years in terms of the global temperature pattern, although you can still see great variation depicted there. Current research suggests that much of this heat energy that has been going on and accumulating over the decades is now accumulating with deeper ocean mixing, and that the oceans are mixing this heat in a greater volume. Also, recent papers from the National Academy of Science have documented that the prolific number of volcanic eruptions that have occurred in recent decades have also probably played out in this temperature signal, not continuing on the same pace that it did or started back in the 80s and 90s. Nevertheless, our climate models applied to all ocean basins and all continents show that we keep the emissions measurements in the models, we keep the transformation of the landscape in the models, where we feature those two parameters in the climate models, they all fit the measured data in almost all situations much better than when we ignore them. So we must account for those things when we're trying to model the Earth's climate behavior. Now, we do have obstacles to deal with when we discuss climate change and its behavior in any public settings where we have a diversity of culture and populations, we have a diversity of economic interests, we have a diversity of environmental interests. And I want to make a point to you about some things that I think obstruct that. First and foremost is, as a population, as a body of citizens, we don't all have the same climate literacy. It would be ideal if we did, but we don't. We're trying to resolve that by putting more climate science into our public school curriculum here, embedded in the earth science curriculum. And there's been a widespread effort to do that, led by a number of our community infrastructure. For example, the National Oceanic and Atmospheric Administration has put a new emphasis on climate literacy. The American Meteorological Society has put a new emphasis on climate literacy. Another parameter that, if you will, or area that prevents more effective dialogue on climate change is our reluctance to talk about our vulnerability to climate. And yet the national insurance industry, our national infrastructure continually has to cope with the extremes of weather and climate and the economic consequences of those. I'll say more about that later. And lastly is, in popular culture, we tend to take a lot of aspects of science, climate change being no exception, and we tend to infuse those in our popular culture in terms of the movies we watch, the music we listen to, the magazines we read. And in those contexts, it's often overly simplified, unfortunately. It's a complex subject that is often overly simplified. Many resources are available to you if you wish to explore those online. The climate literacy resources available to you through the National Oceanic and Atmospheric Administration have been greatly amplified in recent years, and I would encourage you to check those out online. I would also encourage you to check out the national insurance statistics and the FEMA statistics of recent years that show the vulnerability trends to climate change. One of the graphics we commonly look at is billion-dollar weather-related disasters in our country, which have exceeded $450 billion over the most recent decades and continue to go up, which is an examination of, if you will, our resilience to climate change, or maybe more effectively, our absence of resilience to climate change. So that's another resource that you might want to check out. And lastly is, instead of reading about climate change or hearing about climate change in the popular media, I would present the case for you that you go to the bookstore or you go to the library and you find some of the scientific literature that's written about the topic, and that you read more specifically about what the research shows. Some of the resources depicted here, for example, are Robert Henson's Rough Guide to Climate Change, Carrie Emanuel's brief 100-page book on what we know about climate change, and then the more thorough book by Sir John Houghton, a Brit who's written more effectively about this perhaps than anyone, which is Global Warming, the Complete Briefing, now out in its 3rd edition. Online resources that are currently up to date can also be found at the IPCC website, and all of the documents associated with the 5th assessment just released last year can be found there. Lastly, from the standpoint of attitudes, I would just like to say that we've learned with practice, obviously, over time, that as scientists we have some lessons to be learned in engaging the public and students about the topic of climate change. Many people have written about this, including Chris Mooney, one of the more astute writers, who's talked about how we impose our value systems when we interpret science, and climate science particularly. And so I would argue that we need to observe the 5 C's. when we share our thoughts and science about climate change, those 5 C's being our common experience, our core values, our sense of community, our obligations of citizenship, and in the context of having meaningful discussion, our obligations to be civil about it. So, in transition now, why don't we look at what are the changing climate attributes in the Western Great Lakes area of the USA. And what I'd like to do is frame how we're making the measurements, what the measurements are showing, and what the consequences are showing, but using this regional structure to frame this. So if you'll bear with me, there are 3 attributes that are statistically changing in the Western Great Lakes region. Temperatures are changing. Water vapor, what we measure by what we commonly call dew point, is changing in this environment. And lastly, moisture is changing in this environment. So we'll deal with those 3 attributes in the next few slides. The long-term temperature measurements in the Western Great Lakes, here illustrated with the Minnesota State Climate Database, are a compilation of over 200 volunteer weather observers in the state and many communities that have contributed to this record for well over 100 years. Depicted in this graphic is the mean annual statewide temperature taken from all pooled data each year. And what you can see here is the long-term mean value, which is the central horizontal line that carves through the data, here depicted from the late 19th century up to the present time. You can see in the purple dash line the long-term upward trend that's detected there, and then in the light blue line out here for the most recent 3 decades, you can see that the slope or the steepness, the change of pace in temperature, is slightly upward. In other words, it's accelerated in recent decades. Another measure of this long-term temperature record in Minnesota to pay attention to is depicted here by this population of dots in the data that occur over the last 2 decades that are above the 90th percentile line. And indeed, we have had some of our warmest years in history in the last 2 decades in Minnesota. I might further state this is true for our neighboring states and provinces like Ontario, Manitoba, North and South Dakota, Wisconsin, and Iowa all show this same character in their measurements. The seasonality in the temperature change signal is depicted in this set of graphics, and I simply want to illustrate that for the winter season, both the persistence measured horizontally here with the depictions of temperature above the mean value, and the amplitude measured by some of the individual years in the winter season on this graphic is much more emphatic than it is in the other seasons of the year. The other seasons of the year do show positive temperature change, but not as emphatically, not as consistently as the winter season does. This is another common characteristic to our region of the USA. It's also depicted here in the long-term graphic of minimum temperature values for the winter months, December, January, and February. Here we see that it is steeply upward trend. The upward trend here is about 4.5 degrees Fahrenheit per century. That's, by the way, despite the very memorable, long, snowy winter of 2013-2014. One of the coldest, longest winters in the landscape history here, at least in our measurement record, and yet it did little to deter this long-term upward trend in the average winter minimum temperature. How are those changing? An illustration from our Minnesota State Climate Database serves the purpose here by looking, for example, at the change in average minimum temperature that's occurred out in western Minnesota in the community of Milan out in Chippewa County. And here we see in this that the average January minimum out at Milan was once upon a time described as minus 4.3 degrees. But what we use as the modern normal value there is now positive 3.7 degrees. That's what we describe as normal now in that same environment where we once said normal was minus 4.3. And you can see the level of change in the winter months. Average minimum temperatures depicted here is rather significant in whole degrees. We can also look at that in the context of looking at minimum, maximum, and overall mean values month by month. And here we pick a central Minnesota location, which is Willmar, Minnesota, located in Candy, Ojai, and we look at the change in normal values going from the 1971 to 2000 period and then describing 1981 to 2010. And what we see here across the board is prolific positive change. We see prolific positive change in the average monthly temperature values. We see it more profound in the winter months, which I've already alluded to, but we also see it more profound in the minimum temperatures. Minimum temperatures are actually changing more than maximum temperatures. Having looked at the data, it's important to tie in our observation of the world around us and the consequences of these changes in data. So here I illustrate a list of the consequences of these changes in temperature that have led to warmer winters and warmer minimum values. We see changes in depth and duration. Our soils and lakes are frozen. We see more rapid breakdown of crop residues left in the fields by our area farmers. We see that they're having to put on fall nitrogen later and later in the fall season because the soils are not cooling down like they once did. We see fewer obstructions to the outdoor construction season, and many general contractors have remarked about this. They're no longer as disrupted by the weather in the winter season as they once were. We see biology changes. We see changes in the overwinter survival rates of microorganisms, plant pathogens, and other things related to area biology. Fewer heating degree days, which has been a benefit economically because the heating demands haven't quite been so severe. Changing plant hardiness zones. Minnesota Landscape and Nursery Association now markets a wider range of plant species for landscaping in Minnesota than they once did, because with the changing temperatures, particularly in the winter season, we can now landscape with plants that formerly were only suitable for more southerly latitudes. We see a longer frost-free growing season. We see increased numbers of freeze-thaw cycles, which unfortunately is playing out with more damage to our pavements and roads. We see changes in animal migration, foraging, and hibernation behaviors. And we see longer exposure times to molds and allergens, with the season extended for molds and allergens to many more calendar days, and therefore our public health area having to account for this in terms of their caregiving. So that's just a sampling of a few consequences related to these statistical changes in temperature. The second feature of our regional climate that's changing measurably has to do with water vapor. This graphic shows the episodic nature of 90-degree temperatures in our western Great Lakes region, illustrating the number of 90-degree days each year in, for example, the Twin Cities area. It's a highly episodic variable, but you can see that in recent years it's exhibited a fairly high degree of variability, and yet we've had a lot of episodes of heat waves in the Minnesota summers. In fact, if we go back and we look at the officially declared heat waves by the National Weather Service, we see quite a prolific history in the state of Minnesota going all the way back to the 19th century. But there's a distinct character change in what we call a heat wave. In this list in front of you, you will see quite a few years listed, some very consequential, where we've actually had serious livestock loss, or we've even had people stressed, and in fact even some mortality of people with these historic heat waves. But all of the years highlighted in red are all driven by high water vapor content, high dew point temperature values rather than high air temperature values. High air temperature values, for example, occurred in 1936 and 1917 and 1894 in some of these earlier heat waves, where our records show us that the air temperatures actually did achieve 110 or 112, in the case of 1936, even 115 degrees on the thermometer. But more recently, we've also had heat waves, but we've had heat waves with the absence of 100-degree temperatures. This is due to the high water vapor content of the atmosphere. The bar graphs illustrated here, both for the Twin Cities area in the upper right and for Voyageurs National Park down here in the lower left up on the Canadian border, we see these episodes of 70-degree dew points. Now, the reason we use 70-degree dew point here for illustration is because, by definition, an air mass with a 70-degree dew point is indeed a tropical air mass. It is an air mass born at lower latitude. The most immediate consequence of having a dew point that high is it makes the outside air temperature feel even worse than it is. So it inflates the values. And in this context, we go back and dissect summers where the National Weather Service has had to issue heat advisories because the combination of dew point and air temperature has pushed the heat index to values of 100 degrees or higher. And here is a list of those summers when the National Weather Service has had to issue those heat advisories because the heat index has been pushed above 100 degrees. I would point out that we in Minnesota that pride ourselves on our climate resilience, if you will, have endured the highest heat index ever measured in North America. July 19th of 2011, the heat index did reach 134 at Moorhead, Minnesota, which was certified by the Records Committee of the National Weather Service as the highest heat index value ever measured in North America. That was, if you're interested, a combination of a 95-degree air temperature with an 88-degree dew point. Now, the high heat index values do have consequence, and so it's important to understand this feature as well. The higher frequency of heat waves in our region has led to a number of other changes. We now measure different seasonal dynamics of plant pathogens, parasites, insects, and microorganism populations that fundamentally love tropical-like weather, and therefore they do very well when we have these spells of high dew point and high heat index conditions. We've also had a public health concern for this in that we have segments of our population, those with multiple sclerosis, chronic obstructive pulmonary disorder, and other maladies, are hypersensitive to when we have tropical-like air masses and dew points above 70, and especially heat index values above 100. And so overall, there's been a net change in the caregiver community to gear up for this and better care for these people. We've also realized livestock loss, according to those that work in the livestock areas in our region. We've had spells where we've lost a lot of birds with heat stress, particularly in the turkey industry. In the dairy industry, we've lost a lot of pregnant cows due to abortions brought on by the heat stress under these conditions. And lastly, from an energy standpoint, we've become quite sensitive to having air conditioning and controlled environments available to us to escape the heat stress. And so if you look now at all new construction standards and you even look at retrofits or renovations in the northern Minnesota climates that formerly needed no air conditioning, you will find that air conditioning is mandatory in those environments to escape these spells. The third feature of the regional climate changing quite distinctly is precipitation. This is a graphic of the statewide precipitation pattern in Minnesota going from the late 19th century to the current. It's a compilation of well over 1,500 precipitation observers on the landscape measuring daily precipitation. We can see the trend in recent decades is upward. We can also note that the wettest year in Minnesota history was in 2010. That's illustrated in this. We can also see the waxing and waning across time of the precipitation environment on our Minnesota landscape. Back in 1891 to 1920, the region of the state in the light blue and dark blue illustrated on this slide received over 29 inches of average annual precipitation. By the time we got into the mid-20th century, we see that the area of 29 inches or greater contracted to the southeasternmost counties. Then later in the 20th century, it began to expand again, and now in the modern era, illustrated over here, we see that well over half the state landscape calls 29 inches or greater normal annual precipitation. Seasonality in this climate parameter, this moisture parameter, is not as distinct as the temperature seasonality is, but you can see, for example, winters have dominantly been wetter than normal in recent decades. Springs, too, have been dominantly wetter than normal. Autumns have been wetter than normal, and summers have been mixed, both wet and dry. Some of the background normal or frame of reference, location by location in our western Great Lakes region has changed. This is an example from a southern Minnesota location, which once had an average annual precipitation about 27.5 inches, and now it's well over 35.5 inches is what we call normal in that particular region. We can look at another spot on the landscape in central Minnesota and see that at Wilmer, for example, we once called 23 inches normal there, but we now are almost 29.5 inches in terms of what's normal in that part of the state. Embedded in these quantity shifts in precipitation change are some character shifts, illustrated in a recent research by the Intergovernmental Panel on Climate Change, which in the lower map on this slide simply shows you the global landscapes, many of them embedded with a plus blue sign, to say that precipitation has not only changed upward or more, become a larger value in those landscapes, but that there's a greater contribution from convective thunderstorm precipitation, the kind of precipitation that delivers a lot of rain in a short period of time. That's why we have to give more attention to the precipitation climate attribute, more attention to it than simply measuring its quantity, because we need to note how its type has changed, whether it's liquid or frozen. We need to know how the intensity has changed, how much comes how fast, how its frequency has changed, how often it comes, with what duration, and if there have been any seasonality shifts. All of these are important because they play out consequentially on the landscape. One area where they play out is in the incidence of flash floods. Now, in the western Great Lakes region, where we've dissected the history of flash floods across the landscape, we find that flash floods are occurring with greater frequency. We can further break this down by looking at the frequency distribution of, say, 3, 4, 5, 6-inch thunderstorm rains. This graphic illustrates the frequency of 3-inch thunderstorm rains in our region and simply shows that this frequency has been increasing. The new statistics derived from the National Oceanic and Atmospheric Administration, where we've incorporated all the more recent decades of data, show that there's been change in the 5-minute maximum value of rainfall, the 1-hour maximum value of rainfall, the 1-day maximum value of rainfall. And now all of these new statistics are available online in a product called NOAA Atlas 14. And so if you Google that term, you can go to it, find it, and you can look at any point on the landscape and find the newly derived values for precipitation, intensity, frequency, most of which show significant change. Hand in glove with the change in the character of precipitation, that is, being more dominated by convective thunderstorm activity, we must also acknowledge that convective thunderstorms are about who gets it and who doesn't, where it falls and where it doesn't. There's magnified geographic disparity with thunderstorms. We all know that. Some areas get 3-4 inch rains while other areas get entirely missed. As a result of that character change, another feature of the western Great Lakes region landscape we're noticing is that drought, especially severe to extreme drought, is showing up somewhere on the western Great Lakes landscape with greater frequency. In other words, areas are getting missed with the thunderstorm rainfalls. And you can see from this list of all drought years in the region that since the new millennium, since the year 2000, we have had more years with drought present on the landscape than without. Also embedded in that signal, if we look at the attributes of what we call severe convective thunderstorm development, we look at the measured attributes of the atmosphere, such as the lapse rate or change in temperature with elevation. We look at the wind shear aloft, the change in wind direction and speed as you go up through the vertical atmosphere. We look at the mixing ratio. We look at the amount of water vapor in the atmosphere. And what's been done recently by Dr. Harold Brooks at the Severe Storms Lab in Oklahoma is he's found that these so-called severe weather attributes of the upper atmosphere are migrating to higher latitude. Simply stated and shown on this map is that over North America, the common convective thunderstorm attributes that were more frequently measured over the lower plain states like Texas, Oklahoma, and Kansas are migrating to higher latitude and are now measured with greater frequency over states like Iowa and Minnesota and the Dakotas and even the Canadian provinces like Manitoba and Ontario. As a result, this is playing out with more powerful convective thunderstorms over these landscapes. And for example, the Minnesota State Climate Office, illustrated in this sequence of 3 maps, has documented that in southeastern Minnesota counties, all illustrated in these maps, we have had 3 1,000-year rainstorms since 2004. These are the 8, 9, 10, 12, 14-inch rainstorms that tend to massively flood the landscape, all the watersheds associated, as well as the structured landscape, the properties, the homes, the bridges, etc. Another piece of evidence for this northern migration of severe convective thunderstorms is that for the first time in 2010, Minnesota led the nation in number of tornadoes. We had 113 documented tornadoes in 2013. Illustrated on this map is the fact that we had 48 in one day, namely June 17th of 2010. 48 tornadoes, a rather busy day for the National Weather Service. We also use our data from Environment Canada. Our friends in Environment Canada help us document this as well. And illustrated on the upper right here is the first ever F5 tornado documented over Manitoba, namely Ely, Manitoba, back on June 22nd, 2007. The Canadian provinces up till 2007 had never had the convective thunderstorm attributes to powerfully produce a complex of storms that would lead to an F5 tornado, 260 mile an hour winds or greater. And for the first time in Canadian history, that occurred in 2007. And finally, another piece of illustration evidence from our friends in Canada is in the lower right here, where we document up at Churchill, Manitoba on the Hudson Bay, an area of permafrost located 59 degrees north latitude, where many tourists go to watch the polar bears play. Back in August of 2010, they had cloud tops to 48,000 feet elevation, never before seen in that landscape before, and they had a 4-inch thunderstorm rain, the largest single-day quantity of thunderstorm rainfall ever measured at 59 degrees north latitude. And please bear in mind that that rain fell on permafrost. Another piece of evidence is the erratic climate behavior associated with this change in severe and extreme weather. And no better illustration of that exists than the summer of 2012, which is illustrated, color-coded here with a slide from the summer in 2012 across Minnesota and western Wisconsin. The color-coded counties depicted here in orange and red are the counties that were declared by the USDA to be federal drought disasters due to severe or extreme drought. And in those landscapes, there was water rationing, there was crop loss, there were suspended well permits for irrigation. All of the symptoms of drought were in play, declared by USDA, all those counties eligible for federal drought assistance. The plus signs designated over the top of those counties were another more distinct declaration from FEMA that all of those counties were eligible for flood disasters. Flood disasters in the same county that had declared drought disasters. So if you will, polar opposite federally declared disasters, both allowing those counties to petition for federal relief and federal low-interest loans, but for polar opposite climate reasons. That's the first time in Minnesota state history that this has ever happened. And this is an illustration of how erratic the climate behavior has become. Coping with that, of course, is another challenge illustrated here by the hydrograph sequence from the St. Louis River in northeastern Minnesota, which was subject to its all-time record flood crest due to the massive flash flood that occurred in June of 2012 over that part of the landscape, delivering up to 10 inches of rainfall to Duluth in a 12-hour period. The flow volume on the St. Louis River in that part of Minnesota spiked in the lower right hydrograph here at 45,000 cubic feet per second, a volume of flow on the St. Louis River that is analogous to the upper Mississippi at flood stage. That surpassed all previous record flood crests on the St. Louis River, dating all the way back to 1908. That was in June of 2012. Remembering what was illustrated on the previous slide, which was drought, by the time drought had had its effect on that area of Minnesota in November of 2012, roughly 5 months later, the volume flow on the St. Louis River was 458 cubic feet per second. I would remind you 5 months earlier it was 45,000 cubic feet per second. In November it was 458 cubic feet per second, 90-fold less. So in an all-record encompassing examination of the St. Louis River, which dates back to 1908, the volumetric flow record on the St. Louis River shows the two most extreme data points, highest crest, lowest volume, separated by 5 months. Another measure of what extreme weather can do to erratic climate behavior on the landscape. In summary, the changes in precipitation and extreme weather have, like temperature and dew point, led to measurable consequence. We see changes in the biology that we observe on the landscape in terms of diseases, in terms of microbiology, in terms of insects and parasites. We see changes in the moisture-driven exposures to molds and allergens. We see adjustments to irrigation. We see adjustments to drainage. We see shoreline management with the extreme rainfalls we've been getting. We see retrofits of storm sewer runoff systems so they can handle higher capacity storms. We see mitigation of flood potential on many of our watersheds to try to become more resilient in coping with the high volume flows. And we see changes in insurance rates and the way that we have to pay for, if you will, the consequences of these changing climate features. Lastly, and in conclusion, the common ground we have in dealing with climate change is to remember that it's affecting things we care about. The reason climate change is an important science issue, the reason it's deserving of our attention, is because it's affecting things that we value. And you can contemplate that for yourself. This is just an example that many other audiences have provided to me as a climate scientist. This is a topic well worth your attention. It's a topic well worth studying. It's a topic well worth having a dialogue about with your fellow community citizens. And that's where I'll leave you. Thank you.